Today, we're really excited to have Tom Bassett-Dilley, founder of TBDA, which was founded in 2006 to pursue sustainability in architecture. Tom has done a significant amount of work and trying really hard to advance energy modeling, building science, and principles of conservation, along with sustainability. We're really excited to hear today from Tom, and just wanted to also say that he is a founding member and past president of the Chicago Passive House Alliance chapter. So if you're in the Chicago area and you are not part of the chapter, you should definitely check it out. And also mention you guys are in Oak Park, and really close friends of ours are in Oak Park. So it was nice to have that little connection. And with that, I'll turn it over to Tom.
Yeah, so I am in Oak Park, Illinois, made famous by Frank Lloyd Wright. So we have, big shoes to fill here. Yeah, today the presentations on some of our retrofit projects we've been doing lately, one of which was Phius certified, one which isn't, but between the two of them, they gave us a big handful of building science issues to deal with. And so in doing that work, we've been doing carbon accounting using the BEAM tool, which I talk about in the presentation, to really try to understand a little more about the upfront emissions that are inherent in the work. And we've had some really interesting results from that. So I'll try to fit all that in here and not take too long. So as Shefali said, yes, we've been here. I started the firm in 2006, really interested in figuring out what sustainability meant, which we weren't even calling sustainability back then. It was green building or whatever. So 2010, I got Phius training in CPHC, and by 2012 had got the first pass house project here in the Chicago area, and it's been about 20 since then. But the thing is, once you know, you can't go back. At least that's how it was for me, really understanding how a building can perform and should perform to not only be energy efficient, but also be healthier, have good air quality, more comfortable, all the things that we know are important in the way we can design. So anything that we do energy modeling, and we make it as airtight and thermal bridge avoidant, well insulated and well ventilated as we can. So yeah, so this is just a handful of projects. We have a whole bunch going on right now, a lot of retrofits and a lot of new houses, about 40% new, 60% retrofit. And right now it's all single family. So, all right, so I've got two case studies. I'll go back to this. The one on the left is actually project 2, which is a brick bungalow. We have a lot of these in Chicago where it's masonry structure. So the brick is 8 to 12 inches thick, and the wood structure tooths into it, and it's just lath and plaster on the inside, no insulation. Just the brick. So by the end of the winter, you're living in a big ice cube, it's hollowed out. So typically the answer to that mechanically was big radiators to offset the horribly cold surroundings. And then the one on the right is a frame structure with brick veneer on the bottom and stucco on the top. So we had every issue to deal with in terms of making sure these walls would drain and remain dry over time, and get airtight. So yeah, so project number 1 we're going to look at is this Phius retrofit, which we actually got to Source Zero on. There's a Green Building Advisor article on it came out, and there's a Fine Home Building one coming up really soon, I think. So keep your eyes peeled for that for more coverage. But when we got into this, and the owners, we talked to them about Phius, and they said, yeah, we'd love to do it. And yes, we want to get to net zero. We want a really resilient house. We're going to put battery backup in here. They drive a electric car. I'm not going to say the brand. And so we started looking at it and had some conversations with some building science consultants about how to do this. And one of the issues here, like is the issues on a lot of these projects, is that the attic, which you can see the picture of there, is needed for habitable space. So for their program, without doing a big addition, we got to figure out how to insulate that. And the ceiling's relatively low. It's just barely enough space to get the stair up and get, the kids' rooms in the bath, which was the program. And so creating a vented roof there was not going to happen. And so we knew that spray foam would be a solution that we could look at. And so we looked at it. And we talked, when we looked at the building science issues as well with the wall, when you have a cavity wall like this, it's got to drain, but it's, there's moisture in that cavity wall, and we don't have the opportunity to address the drainage plane because that would require removing all the exterior materials, the brick and the stucco, and getting a new drainage plane. And this is a historic protected building, so we couldn't touch the historic materials. So the decision was made, we decided to get a couple inches of foam to control condensation and become part of the airtightness strategy against the backside of the sheathing and against the underside of the roof deck. And then we stepped a new stud wall in from there on the first and second floors and filled all that with cellulose. So basically using as little foam as we could, but it was a lot in the roof, especially when we got our almost 60 up there. This picture here of the basement, we've got the dimpled mat going in. Those little pipes coming in underneath the window are the stub outs from the ground source heat pump, the geothermal well. So that's how this house is heated and cooled. So here you can see two stages of the interior retrofit. The foam was put in a couple inches. You can see the stud wall standing in from that. And then the next is the later stage. After the foam was in, we completed the air tightness with a run of aero barrier. So that's the aerosolized material that is pressurized with a blower door, depressurized, I should say. So basically, no, pressurized. So it's going to blow the sticky stuff into all the voids. And, so after the windows are installed and caulked and all your penetrations are sealed, do the aero barrier and get up to your airtightness. Now, funny thing that happened was their blower door reading was a lower CFM than our third-party Phius rater. Apparently, it had gotten kind of caked up with all their sticky stuff over time. And so they thought they were good on the airtightness, but then our rater came and tested it and saw that, no, you're not quite there yet. So we had to come back and troubleshoot some very difficult areas up here at the kind of roof to wall connection. There were some places that were extremely difficult to get to around dormers and, all those corners that are being turned, very tricky. So, so after a couple of returns, we got to, 0.06 CFM per square foot. So that's number one. We can kind of come back and look at details if people have questions. The brick bungalow is different though, because there is no cavity. Oh, and I just want to point out one more thing on this section. A couple of things we did really rigorously were draining the walls and flashing the walls. So the brick, we had to take off the bottom 3 courses of brick to get new weeps in, making sure that we didn't have moisture accumulating at the bottom of that wall. So, could put flashing in, get new weeps, and the moisture could get out. And then at that horizontal screen course there above or below the second floor windowsills, that's completely new, flashed up. And we broke out the bottom couple inches of stucco, got flashing to come out and over, just draining all that stuff. The bay windows that projected there on the corner first floor, they required new step flashing to be put up, some more brick taken down. So it was, all these little places that could lead to failure, we tried to address. Fortunately, the big prairie style roof up on top is a big help. So the brick bungalow is a different animal because you can insulate to the inside of the brick. There's no cavity to worry about draining, but you got to make sure that the moisture doesn't want to come in through, solar drive or just the brick being a sponge. But then here's another attic that's, look at that framing, right? How are you going to really get membranes up there to make that airtight and preserve your headroom. So similar situation here, except we took the foam from the roof down the knee wall that came up above the attic floor level, and then transitioned to all cellulose below that. But the first thing we did was treated the wall, the back of the brick wall, with a spray, fluid applied sprayed membrane called Viscon, which seals it all up. And so the moisture coming in from the outside stops there. And then when we did the wall, we stood the studs off of the brick by about 1 inch, and then put Intello on the inside face of that. That's our smart vapor retarder. So moisture is building up from the brick. It'll be able to, diffuse back into the brick. It sort of stops it from coming in and, soaking things. But if it's, trying to explain a smart vapor barrier, keeping the moisture out of the wall is sort of a one-way valve. So it's keeping the moist air in the winter from getting in and soaking that brick as well. So yeah, new windows, new mechanical systems, ventilation, ERV, the whole bit. Even though this one's not Phius certified, we still brought our tester to say, to look at how we're doing on this thermal envelope before we put the cellulose in, and before we seal everything up with drywall. And so he's going on in there with the spray gun to just show where where voids were in the foam, and with the smoke gun at the windows, just identifying where leaks are happening. So whether we're certified or not, we want to get our quality control during construction on all projects. So for this one, we did do the aero barrier as well. We got it below 1.5 ACH. And so it's not quite, it would have to have been about 0.98 ACH to reach Phius, but this was enough to qualify for the all electric homes incentive. And so you see it, they ran it for like 1.5 hours, and it gets expensive as you keep blowing that sticky stuff. And it seemed like there were some weird breaks that we couldn't find. So we stopped at 1.5, which is, a big help. The previous before of 2.5, that was after the foam was in. So that's when they started doing it this day. It was more like 8 to 10 ACH, like most of these old homes that we test before we do the installation. So that before is not a pre-construction baseline. It's after a lot of the work was done baseline. So here we got some Phius modeling results as well. You can see for the original kind of standard, we're not nearly there with heating demand, heating load, but I am quite sure this house would make the new Revive program, because it's more about resilience and less about just envelope. How am I doing on time, y'all? I don't want to run too late.
You're doing great.
5 minutes?
I think 10, right, Kim?
Yep.
Yeah, 10 minutes.
Okay. Great. Okay, so I want to talk a little bit about the embodied carbon aspect of this, because we try to avoid foam. That's been, getting lower embodied carbon has been the push here. And when we do new construction, we're wanting to use straw for walls and roofs, cellulose at least, or hemp or wood fiber. The low grade, foam glass is better than EPS even. EPS is better than XPS. So, all these decisions, and it's easy with new construction to plan for that and make that happen. What we're finding is that with these retrofits, when we have these inhabited attics, and sometimes with a cavity wall, we're not avoiding the foam. So how are we doing? Is it worse than a new construction? Is it fine? So the beam tool is what we've been using to do that measurement. And this was made up by Builders for Climate Action. It's free or small donation, I think. And this is basically looking at cradle to gate emissions. This does not include the energy of installation or the deconstruction or disposal, which is still important. But so just as an example, this is us using the software, but I think you've seen this kind of thing if you've looked at architecture's 2030s embodied carbon. You know, the impact of just different insulation materials. We've got R41.8 because we're using our sample house, and that was the wall that we had designed with, I think it was 12 inches of straw. So when you look at that, the upfront emissions are measured in kilograms of CO2 equivalents, because it's not just the CO2, it's also the, let's say, the gases that are used as blowing agents for foams, other emissions that are captured in an EPD, environmental product declaration, are baked into the software so that when you choose a material like wood fiber or hemp or fiberglass, you have some selections you can make, a particular brand name or sort of industry average, et cetera. But this is showing you kind of the impact. You know, this is why we love straw. It's just incredibly low amount of energy to bring it from a plant that sequestered carbon to turn it into a building material that then can be locking in that carbon for 100 years. Cellulose is also our great negative. And then as we get up into the fiberglass mineral wool, you can see we're into the positive territory where we're not sequestering carbon, we're using it. And then when you get into the closed cell foam, which is the far left, the blowing agent HFO is a heck of a lot better than HFC. And so you can see that massive difference in impact if you choose the wrong foam. So that's we ride our contractors that to give us a submittal, and we show up when they're getting ready to blow the foam, just to be 100% certain that they don't show up with the wrong thing, because it happens so often. I mean, for some reason, XPS insulation is on the shelf at Home Depot, but EPS is not. And so we've had probably half of our concrete jobs where the concrete guys will show up with a bunch of XPS because that's what I could get, and we've specified EPS, we've told the general about it. So kind of, it drives us nuts. But so when we did our carbon calculations here, what's really great is it breaks it out into different components, and you can see where we're spending carbon to build this thing. And because we didn't have our carbon pure concrete available in our service area when we did the slab, the footings and slab include both the garage and the new basement slab, which we had to take out the old one, put in some new insulation, and put in that slab. So you can see that the concrete is pretty big emitter. But you look at exterior walls, and it's not, because that cellulose is negative, balancing out some of the positive of the foam. The roof, though, you can see is a big one. But shockingly, the windows take a lot of energy. We used fiberglass UPVC composite, triple glazed from Alpin. But what we found, I have a comparison slide if we have time later, you can look at it. Whether you choose all wood or wood aluminum clad, it's not making that big a deal. Glass is a big deal. So so you can see kind of where we're at with emissions on this. And what we did is we translated this to kilograms CO2 equivalent per square foot, so we could have a baseline to compare different buildings. And you see this one's coming at 6.6 up there in the upper left. The retrofit of the bungalow that had a lot more cellulose and a lot less foam and didn't have a garage came in at 4.1. So that's a heck of a lot better. And Beam gives us this little sliding scale of storing, a building which is storing carbon, or it's low upfront emissions, average or high. And we like to get to low, obviously. And I think everything we've done has been low or maybe low side of average. But getting to actual storing is really tough, especially if you put windows in your building, because look at this. Again, the windows are the biggest emitter in this house, which, it needed. But look at the exterior walls. They're actually storing. So that little bit of foam up above was offset by all the cellulose below. So this has been a real eye opener for us. And the place, I'm going to come back to this slide. The place that it really got interesting is when we took our old, our design of the new house. So this is a new construction modeling up on the top, where we're looking at the embodied carbon of our old retrofit, or sorry, our old recipe, where we've got, regular concrete slab, and we've got 2x6 wall cellulose with 5.5 inches of EPS on the outside, cellulose in the roof. Everything else is pretty much the same with windows and whatnot. But then we're at 15 there for new construction, compared to the 6.6 or 4.1 of the retrofit. So obviously, when they say, oh, the greenest building is the one that's already there, there's a lot of nuance there. It's not necessarily true, because going to the middle, when we swap out the concrete in the foundation for carbon cure concrete, low embodied carbon, and we swap out our slab on grade for a concreteless slab. So basically, the same insulation, the same vapor barrier, but a couple layers of Advantech plywood with flooring on it. We've eliminated, 1,000 square feet of concrete, and then all cellulose, double stud cellulose wall. We're down below 10, so that's pretty good. But man, when we go all straw and we use foam glass instead of EPS for our concreteless slab, and we use all wood windows, we're down at 3.3. So that's like, it can be done. And it could be even a little better if we had less windows, or maybe with straw, if you put more, it's better. So if we did thicker walls, it'd be even better. So the retrofits are coming in great. But if we had one that we didn't have, where we could have a vented attic, we just use cellulose up there, cellulose in the walls, then we would be getting a situation where we could do better than our best recipe new house, but it's in that range. So I'm not suggesting we go out and tear down houses, because most people won't be building straw houses with mineral wool and all that. In fact, for comparison, if you look in the lower right, if you took a just built to code level insulation, but you did it all with closed cell foam, which I've seen this as a suggestion in building sections from builders, you're up above 18 if you're all HFO, but if you use HFC because your insulation guy gets it cheaper and you're just doing things quick and dirty, you're up at 30 kilograms CO2 per square foot. So, and that's generous. I mean, I think that a lot of the stuff that we put in there would probably be higher in terms of finishes and all that. So, yeah. So anyway, that's kind of putting it in context. Well, this is, sorry, a little bit of a eye-crossing slide, but you can see the green line there, the Chicago retrofit with solar. When we put embodied with operational carbon over a 30-year life cycle, this is kind of what we're seeing, that it takes so little to do that work of the bungalow retrofit. And if we put some solar on it in year 4, is what this green graph is showing, we're doing great. Compared to our old Phius assemblies, we're better than that, even if we did a Phius full, certified house. The Source Zero retrofit, because it's carbon operational net positive, is the yellow line going down. So there, the question is it worth putting a little more carbon into it and offsetting that with solar? In 7 years, you've recaptured what you would have done if you could have not done foam and, whatever you might have done to reduce your spend, compared to the green line. But then we're down, 0. So this has to do with when we're trying to meet our climate goals, 2030, 2040, 2025. So yeah, this is kind of putting it in context. The average code compliant house we put at the top is probably higher at its starting point on the left, but that's basically taking our same model and just putting average consumption data from the energy EIA, said it. So yeah, so that's that. Yeah, kind of putting it in context. So yeah, just to go back to this slide quickly, when and why we foam. When we have that habitable attic, roof. And, you know, when we've got existing cladding without back drainage, these are things that lead us to that. This little overhang here, you get this a lot of bays, projecting bays and whatnot. These are places where it's possible to do it without foam, but it's can be riskier. And then of course under the slab. So yeah, I think that's all I got. There's some contact info, and I'm happy to take questions or you know, whatever you've got.
Yeah, I mean, there's amazing questions in the chat already. I just want to say, like, Tom, wow, like amazingly helpful and useful. And we're going to do a quick sponsor announcement. We'll be back for questions.
Okay, should I unshare? Or
Sure. Yeah, that's perfect. Tom, that was amazing. Thank you very much. And there are lots of great questions. So I'll be quick. I want to thank the fine organizations that make everything possible here at Passive House Accelerator. So a big thank you to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thanks to our founding sponsors, 475 High Performance Building Supply, Ingwe Architecture, Partel, Rockwell North America, and Zola Windows. Thanks to our champion sponsors, Bewizo, Cascadia Windows and Doors, European Architectural Supply, Facro, Icon Windows and Doors, Intelligent Membranes, and Source 2050. And thank you to our patron sponsors, Brennan, Holstrom System, Inotech Windows and Doors, Lamelux, RDH Building Science, and Sanderson Sustainable Design. A big thank you to our sponsors.
Thanks, Zach. So as said, there are some really great questions in the chat. Kim just put up kind of our order of questions, our virtual list of, line of people asking questions. So if you're still on the call, please unmute yourself and ask your question. So we're going to start off with Nate Trick. Are you still here?
I am.
Great.
So my mom lives up in Central City, Colorado here in a 150-year-old brick house. And, same story, no insulation, just lath and plaster. So when you start spraying the spray foam over that, and then you showed the Viscon, I put my question on there before I saw you doing the Viscon over the brick. Would the Viscon, you said you were using spray foam as an air sealer, but could you just do the Viscon and then pack your dense pack cellulose in behind the Viscon and not use foam at all?
that's what we did. Yeah, it's Viscon as our air barrier and moisture barrier against the backside of the brick, and then all cellulose to the inside.
Yeah.
So where we have foam, yes, we don't need that Viscon because it's basically doing that. It's a waterproof.
Okay. So that's where I was like, if you wanted to avoid the foam up in the attic, could you go with the spray applied Viscon and even use the fibrous one that might fill any gaps, or roll apply it and then put your cellulose in behind that in the roof as well?
Yeah, but you need to then get fluffy insulation, which is going to take about twice the amount of space. You have to get ventilation above it to meet code. So you're gonna frame down from your existing deck somehow, and try to create clear vent channels, which are interrupted with blocking and hips and collar ties, and you're gonna lose, a bunch of space inside, and then you have to get a continuous vapor control membrane like the Intello, and it's gonna be punctured by all the collar ties and all the discontinuities in the roof plane. And so, I mean, so basically the 1-2 punch there is we can't get clean venting above, unless we go above the roof, which with historic buildings, we can change the profile. And then we also we're relying on a really great control of Intello up there, where all the stack pressure of the house is coming up, trying to push that moisture up into the roof. So we got to get a really good vapor barrier or vapor control layer, and that's super challenging. But when you also lose your ability to have your rooms, because you've lost your headroom, you don't have code clearance over the plumbing fixtures, and you've lost your habitable size of the bedrooms. Those are the factors that pushed us into the foam. But theoretically, it's doable. It's just, it would take probably demoing out a lot more of the roof and redoing the collar ties and just having a lot of really great taping.
Great,
Thanks.
thanks. Bev, you're up.
Yeah, Tom, great presentation, first of all. My question's around aero barrier. So I think the examples you're giving were guts, right? And I would think aero barrier is a pretty small piece of that cost. Is that, like, what general sense of cost are we talking about? And it sounds like you're going back to it over and over, even without the tweaks and problems you mentioned. Just any comment on that would be helpful.
Yeah, the aero barriers, a couple $1,000s, I think. And it's going to depend on the square footage of the building and also how porous it is. Like one time we were looking at putting it in before the foam, and the aero barrier people said, no, that's crazy. The wood is so porous and so like hairy, it'll just soak in. You'll put 55-gallon drums of this stuff into the building. So do your best, foam it, caulk it, seal it, and then and let's let this do the rest for all the weird things that you couldn't see or get to. So yeah, it's a pretty friendly thing. It's easy to think, oh, we'll just sort of fall back on that, but you really do have to, caulk and seal and really take care of everything still. It's not like it lets you off the hook from having to tape and carefully manage.
Sort of follow-up question, in a non-gut situation, have you seen aero barrier used successfully? Like I know of a couple examples, but you have to be really careful protecting everything and you have to cover everything really well. But
we haven't done it, so yeah, I think it does definitely leave a sticky film, so it could be pretty rough. But yeah, I feel like when we're looking at retrofits, we typically say to owners, who are looking to say decarbonize and really lower their heating and cooling demand, we're going to look at your roof and we're going to figure out a solution to get a really good air seal there. And that might take tearing out your ceilings so we can do that. But if you don't take care of the roof, that's your big lid, and then take care of the basement infiltration areas. I remember, in the building science literature, like you look at the pressure of the building, it's, most high up above and most low down below. So if in the middle, if you're not dealing with all of that, it's less impactful from an airtightness perspective than the very low pressure and the very high pressure. So yeah, we basically are really rigorous about that. It's usually easy in basements, and it can be really tough in attics. But yeah, so I guess in those cases, we usually wouldn't need to go to the aero barrier to solve it. We do it with membranes or something.
thanks, Tom.
Thanks, Bev. Paul, you're up next. I know you put in a couple of questions here and a comment, so if you want to just do all of yours now since you're up.
Yeah, thanks. Hey, Tom. Thanks for a great presentation. You are validating many, if not all, of the situations that we've run into in our retrofits. In our particular house here, with a historic house, we have great brick, impermeable brick in the front and porous brick in the rear.
Yeah.
Right. So we have our air barrier at the interior, and we use cellulose. And talking with Joe Stieberg, he said, if you got good bricks and it's airtight, you can put as much insulation in there as you want. However, not necessarily the situation for permeable brick. So the question is, did you do any brick testing? If you did, what did you do about it? And I just wanted to say that the last comment, which is not related, but I'll let you speak, is about closed cell spray foam in a situation like a roof situation. Like we have clients that have just put on solar panels, so we have it's going to be a non-vented roof, and code compliance is going to require us to do spray foam. So we're running to that same situation.
Yeah, we did not do brick testing. We knew we were going to be putting the Viscon against it and dealing with the moisture on the backside. It's a safer thing to do. We assume that the brick is somewhat porous. And, you know, we talked to Coda Building Science Corp about it, and he's like, yeah, you could do that, but what are you going to find? You're going to find a certain amount of porosity. And, you know, almost certainly if it's not difficult to spray it, then just spray it. So it's kind of what is the best and least risky thing. On the other project where it was a cavity wall, didn't matter how porous the brick was, because it's, you know, it's got back drainage. And then, you know, like I said earlier, the thing that really is a big relief to think about is how big those overhangs are on that house, and even intermittent trims like stream courses and, you know, the various bumps and sills, those matter. And yeah, we had Steve come and talk to us at the Passive House Alliance Chicago about masonry retrofits years ago when he was in town for building science fundamentals, and yeah, he was talking about all those little projections and the things that modernist architects hate. I mean, when you're doing a really, you know, glassy, flat building, hopefully it's not a material that takes on water, because it'll be finding its way in. So yeah, I mean, I guess the Viscon to us was the answer.
Great, thanks, Tom.
Paul, did you get to ask all your questions and comments?
Well, I can talk about aero barrier in our situation. We have a row home, and if you can keep the air barrier inside your house, no problem at all. But if you've got a leaky situation with shared joist pockets and a roof that might be sitting on top of the party wall, it could go over into our neighbors. So that was our situation. It was a you know, but my first thought goes to, man, we could really get into trouble here. But we didn't know. We just did what we thought was the right thing, and then our neighbors started to have some white misty stuff landing on his head, and he was freaked out, as he should have been. So we shut it down. So it's something to be aware of. It's not, you know, it is not a it's a great process that worked well for us, but it's not for every project and not for every situation.
You know, I just wanted to throw one more thing in. The previous question was about Colorado retrofit, Nate, and I gotta say, we were designing a house in Fort Collins, and I was stunned at how much less we had to worry about moisture because of the low humidity. So
Yeah,
a lot of the things that I'm talking about are so much driven by a Chicago mindset, which, you know, applies to, I think, a lot of the country. But yeah, when the humidity really goes down, it's a different.
it's so dry here that, like, yeah, you know, back in the 90s, there was a huge, you know, black mold issue with EFIS, you know, on the backside of the EFIS and stuff.
Yeah.
So a bunch of homes, brand new McMansions, had to be, you know, had, you know, black mold buildup due to moisture condensation and stuff behind the EFIS. But traditionally, yeah, you've got a lot of vapor drive in the wintertime going, so that's where the Intello stops it. But, you know, if you have like an Intello type system, I think it dries. It's the ability for your house to dry is so much better here. It's amazing.
Yeah.
Great. I think we have definitely time for a few more questions before we have to do some behind this, some other news updates. So I think I'm up. So just because I know there's a lot of historic buildings in Oak Park, this Viscon project, do you know if they can be used on historical properties? Traditionally in New York, either local landmark preservation or state SHPO has a hard time when something is spray applied to historic brick and like potential for damage. So Is this something that you have been able to use on historical properties?
Yeah, well, the local district only has purview over the exterior. So if we use something sticky on the interior, you're right, it's not reversible, which is the principle of preservation from the Secretary of Interior standards. So it only becomes an issue when an owner is going for, let's say, a tax assessment freeze, which then has purview over the interior as well as the exterior. But usually they're interested in preserving the visual appearance. And so if there's something behind the visual appearance, like aero barrier, I think that it would probably be a pass. But it also, I think, will depend on the level of importance of the interior relative to the exterior. I mean, if you did it on the State House or something, it might be a no, versus a single family house.
All right, Molly, are you still here? Molly S.
Yes. Hi, Tom.
Hi.
My question is, in an old house, in a retrofit of an older home, the area that I'm talking about was built between the 20s and the 40s. If you're not building out the attic space, but you want to open up ceilings above, for example, you're creating a great room and perhaps they want the master bedroom ceiling opened up and vaulted.
Yeah.
Does that allow for better insulation situations?
Well, I guess it depends on where the thermal boundary is. If you've got an attic with a flat floor and that's where the insulation is, you're going to raise it in certain areas, then you're going to have to figure out how you transition that insulation plane, up an attic wall onto a higher surface. So, I mean, it's doable. I don't know if I don't think it doesn't make anything easier, but it can be solved. But I think it would really be a study of the section to see, how you're going to get airtightness. Anytime you take an airtight layer and you bend it, fold it, penetrate it, you make it more. You just have more work to do. So it's, but I said we've done it where we've had, areas in the house where just having the flat ceiling and the vented attic is fine. And then we come into a, special space, great room kind of situation, and we're going to raise it. So, that could be planned for. A little easier in a new than a retrofit, but still with design, we can solve anything.
Yes. Okay. Thanks. I appreciate it.
What kind of software did you use for carbon capture? To capture the carbon. In the district we're using policy to reduce or at least kind of try to track the carbon as best way we can. So I'm learning more and more about softwares that are doing a lot of the calculations for carbon capturing.
Yeah.
So what did you use?
We're using Beam, which is from Builders for Climate Action. I know a lot of people are using Tally and EC3. There are some other softwares out there which I haven't used. We learned Beam and kind of stuck with it because it was what we learned. It was fairly easy, and it's nice to have a pretty good database of EPDs baked in. So, but yeah, I think other people might know more about other programs that are out there and how they're different. But those are the ones I know. Tally and EC3 and Beam are the three that I really know best or have heard of.
Okay, great. Thank you.
Sure.
Thank you. And if anyone is able to put any other links in the chat for Ashley, please go ahead and do so. That'd be great. Next up, we have M. Reynolds. M, are you still here?
Yes, I am. My question was just quickly about the non-concrete slab that Tom mentioned. And I've had one answer from Prescott Perez-Fox about fine home building for a concrete-free slab. I just curious to know what it is and what it's called commercially, and is it available nationwide?
Yeah, well, it's basically something that's custom built on site. normally when we do a slab on grade, or historically when we've done slab on grade, it's, you know, starting from the excavated ground, there's the gravel layer, and then insulation, and then the vapor barrier on top of that, and then the concrete slab. So when we want to get rid of the concrete, we need to create a really good level base. And so we've got the ground and then a gravel layer, and then we do a layer of fines that we level out with a laser ball. I'm trying to remember if I have that. I have some pictures of it, but not on the slide deck that I just had up. So then you have this nice flat level. Then you put your insulation and your, well, what we do is 2 layers of insulation. So we do a first layer of insulation and then the vapor barrier. In our case, it's like a 10 mil Stego, I think, Stego wrap. And then the next layer of insulation, and then 2 layers of cross-laminated plywood. We use Advantech because it's very stable. So that gives you 1.5 inches of solid wood, basically. And then on top of that, we can do a wood finish floor, cork, linoleum, you know, tile, whatever you want, basically.
And you don't ventilate any of that timber in there?
No. You've got the vapor barrier, and then you've got insulation and then the wood. And so it's diffusion open to the interior. So any moisture that gets in, I mean, you have to tape like crazy, and you have to think carefully about how plumbing works underneath there and how you plan for that in the gravel layer. So if you go to a fine home building or Green Building Advisor or Journal for Light Construction, you search for these. I think they each had at least one article. And like, for instance, I think Geologic did a house in Maine where they did like a 12-inch sand layer to put their plumbing in, and then they did their insulation and stuff. So there's some interesting variations on it, which are worth checking out in the literature.
So, but what's the elevation above the ground level? Because
Well,
you've got
always
runoff.
6 inches maybe. I mean, 6 inches a foot, you know, whatever. It's I mean, 6 inches is code minimum for any wood above grade. We usually are like a foot up.
Yeah.
When we're doing slab on grade, we're usually designing for aging in place, and so we're trying to create a house that's relatively close to grade.
So what's getting you up above grade is the insulation.
Yeah, you know what? I'm going to share my screen because I do have a
That's really interesting.
picture of this. We click on here so we can back up. So if you see on, do I have it?
No, I didn't see it.
Oh, you know what? It's in the later ones after the real show, the after party. Okay, so here you go. The one on the ones on the right here are 2 different versions of concreteless slab on grade. And if I just zoom in on this, you can see it a little better. See if I can slide over here. Yeah. So here's a detail showing the kind of the control layers. So we've got gravel and then fines, foam, and then vapor barrier, Advantech, finished floor. Then here we're doing it, instead of using foam, we're using a bunch of foam glass. Instead of using EPS, this is foam glass, which has a lower R value per inch. So it's a deeper buildup, but it's got lower embodied carbon. So
the footings are still concrete. They're still warm.
the footings are still concrete. We've been looking into wood, permanent wood foundations. There's also some articles on Building Science Corp about that, and on Journal for Light Construction, or Phius Zero maybe had it. So
people in England are using rammed earth, trying to, but it's tricky with.
When I've done rammed earth in the past, it had a pretty good amount of cement in it. So it's, you know, not quite as much as concrete, but yeah. In fact, the one rammed earth house I did was in Ventura, California, and I noticed somebody was on here from Ventura. When I used to live out in LA, I got a crazy project, but anyway.
Okay, thank you very much.
Sure.
Awesome, thank you. And it looks like I skipped Douglas, so if you're still here, it's your turn.
I'm feeling all hurt now.
Sorry.
Uh, Tom, have you used, back to the slabless construction, that can also be done with a frostproof foundation, and just run the insulation up and the formwork up as tall as you need to go above grade.
You're right.
And the one issue that I've heard with the slabless foundations is be compact very, very well. And unlike concrete that flows out level more or less, the Advantech is not going to do that. So screeding it very, very precisely will make your life go better. My question is, Tom, have you used any straw in retrofits?
No, I haven't. And it's something I'm really interested in. When I was at Greenbuild, I was talking to Chris Magwood and I forget who else in the straw part of the trade floor. And apparently there is somebody in Canada who's got that you can basically use, somehow you can blow it in. But I think the difficulty is that, when you're using it like what New Frameworks does, where you basically take a bale and just compress it and then hit it with the weed whacker, in a wood frame. That's pretty straightforward. I think the difficulty is if you don't really have it fairly densely packed, it's going to settle. I just don't know how you do that in a retrofit. Have you seen it?
No, I haven't. Not in a retrofit. And you think back to half timber construction, and that's what their insulation was.
Yeah.
But I don't think they were really packing it very much.
Yeah, and I think it was more like a binder with the plaster, right? And less of a solid kind of material. But yeah, it's basically, yeah, with the plant-based buildings is kind of the mindset for me. So whether it's hemp or wood fiber, wood fiber is great too. But then, cellulose is pretty hard to beat. Around here, there's a lot of cellulose installers. In Milwaukee, we struggled actually to find them. It's very weird. Maybe it was just the GC we were working with, but anyway, yeah, I think if we don't have straw yet, at least we have a lot of good other alternatives. And I think that it's important to go back to the EPDs and look, the hemp numbers that I showed on that one slide, I think there may be some out there that are better. Again, it's a question of how much energy does it take to turn it from the plant growing in the field to the material that you're going to put in your building. Lumber takes a decent amount, but once you have leftover wood chips, it doesn't take much to turn that into wood fiber board. Or blown fiber, wood fiber insulation like Timber HP is doing.
Mm-hmm.
So, anyway.
All right, thank you very much. I really appreciate you highlighting the embodied CO2 in materials and looking at that as a very important point to your designs. Thank you.
Yeah, appreciate it.
Great, thank you, Douglas. Next up, we have Mario. Mario, are you still here?
Hello, can you hear me? Hello?
Yeah.
Yeah.
You're the one
Hey, how are you? Good morning. Sorry about that. I had it in landscape and I had to switch it to portrait and putting gas in the truck. Tom, good morning. Nice to meet you.
Yeah,
I want to say I got here late to the presentation. Unfortunately, I was looking at we're doing some lead testing on a paint job here in the desert. But I wanted to ask you specifically. It seems like this was the one I was waiting for. This presentation, the retrofitting. I've done remodeling since 2013 and a big Airbnb boom out here in Joshua Tree. And so I was actually my question was specific to if you've had any practical experience. I can look at the 475 smart wall, all the different kind of things and how to retrofit for passive. But what has your experience been with insulating installation on retrofits for slabs, for footings, because obviously you can't remove the foundation to add insulation underneath the slab. So do you just try to do you dig out alongside the footings, you know, side by side, so you don't compromise the strength of it, and then you sort of add foam? And then how do you tie that in to the new retrofitted envelope? How do you kind of like bring that all together?
That's an interesting one. Would this be like for a house with a basement?
Not specifically. Most recently, I was working on a house from 1927 in Mar Vista, Venice.
Yeah.
And we were getting so much because it's all like silt, right? So when it would rain, it would fill up in the crawl space. But I was just asking myself, even for something here in the desert, we probably don't go deeper than 18 inches for footings, especially on the older houses. Maybe on the newer houses, probably all close to 24 inches. But how, say if I were to buy a property and retrofit it, what would I do? Just cut back, dig it out, add insulation?
Well, yeah, you know, it's basically every building that we've dealt with so far has been unique. So, but I'll say that generally our decision tree is where the building meets the ground. Is it dealing with moisture right? Does it have any thermal barrier? And if the answer is no on those, then we absolutely got to fix it. And so then the question is that either tear it out and redo it. And if it's concrete, you're spending a lot of carbon on that. So we don't want to do that. Then it's like, can we go over the top of it? Like with a dimpled membrane and then insulation and new flooring, like basically almost like our concreteless slab assembly. You know, then you're going to raise the finished floor by, 4 to 6 inches. So, or let's say 2 to 4 inches, whatever. But then you can have all your moisture and vapor control. You know, for us, we got to worry about radon also. You can do all that on top, and then you don't have to spend all that energy on or embodied carbon on concrete.
Sure.
So that would be one approach. For the exterior, like stem walls and whatnot, yeah, you can insulate on the outside. But then you've got insulation sitting there, you got to cover it up. And so that's always a tricky detail, especially if you got to worry about termites or, whatever. And then if it's sticking out, if you're retrofitting the wall, adding insulation to the outside, then you can get all that to align and it could be really nice. Otherwise, you've got
a single plane
to work with there. So it's always, are we going inside or outside? Both can be done. Outside generally gives you the opportunity to reflash everything and take care of moisture in one go and eliminate all your thermal bridges over studs. So I would say that, exterior, if we can do it, we prefer.
Yeah. And I love that you mentioned carbon cure. Awesome. I mean, I get it, but I put the YouTube, the CNN report that they did with carbon cure in Atlanta. They were building that parking structure, or they were doing some building. That was really interesting. Have you heard of anybody using CLT as part of like the slabless construction? Like you were explaining, like using different layers, but has anybody used like mass timber as like for slab materials?
No, not that I've seen in that situation. I mean, certainly you can do a mass timber slab as a floor in a building that's mass timber, but it's not carbon sequestering. You look at the EPDs, it takes a fair amount of energy to put those things together and to adhere them, and so they're not carbon negative. It's certain things like cellulose and straw and wood fiber. The more you put in the building, the more you're storing carbon. So that's great.
Sure.
But
sure.
With wood, it's got a very, very small positive carbon footprint. So
sure.
So mass timber is not a solution. And yeah, I mean, I guess my question would be, why use all that wood if you can do it in 1.5 inches? Why do it in 3.5 inches?
Yeah. Well, I mean, I'm definitely, I love that your presentation covered so many aspects, especially me as a remodeler. It covers so many different, you covered so much. But I'm a big fan. I just want to get it out there. I can't wait till Timber HP starts shipping out west. When they kick out over here, I'm a big fan of theirs. I'm a big fan of carbon cure. Obviously, try to get away from the concrete as much as we possibly can. But all these little kind of changes and all these moves towards that are making it a lot better. And obviously, with the fires out here in Pacific Palisades, I can't go surfing. I can't go surfing in Topanga because they have the beaches closed off from all the chemical runoff from the toxic materials that are going down into the ocean. So now I'm stuck to going to Orange County and San Diego County to go surfing. So I'm kind of thinking of all those sorts of things, and
yeah. Yeah, we lived
You know, at
in,
least,
we lived in Venice for 9 years, right
okay.
there on the beach, and we were there for the first Malibu fires and did a couple fire rebuild projects. I cannot imagine what the city's going through now, and
Yeah.
you know, I guess, you know, going down to Dana Point's not that bad, right?
No, I was actually going to take off Wednesday last week and go down to Dana Point, just take the whole week off that I didn't.
Yeah.
Yeah. Well, thanks a lot, Tom. Thank you so much. This is such a great presentation. Thank you. Thank you very much. Thank you all. Kim, Zach, thank everybody. You all have a great day.
Thanks, Mario.
Yeah.
We have room for one more, and I'm putting Tom's email in the chat. If anyone has other questions, feel free to reach out to him. Final question today is from Ian, if you're still with us.
I think there were two Ians, but the brick cream thing, I think you said you hadn't seen it. It was on one of the Passive House Accelerated calls a couple of years back. Can't get hold of it in Canada, but
Is it like a paint essentially, or?
yeah, it's like it seems to be just a more intelligent water to stop more water penetrating into the brick.
Yeah, I mean,
It's
I know we've like Thompson's, you know, penetrating water seals can be put on. I don't know their effect on once the moisture does get into the brick and capillarity brings the moisture in, especially at the grout joints where they're even more porous and pulling that moisture into the wall. If you put a coating on and it is preventing that, you know, diffusion out or limiting it in some way, would be my only concern. But I'm sure that that's the that they know this, and so they would choose the right kind of thing. It's like, you know, using lime plaster instead of Portland plaster.
Yeah.
For, you know, diffusion.
Yeah, because it was more your comment earlier on the solar gain of the bricks. It's kind of because I know I'm in a brick house and you do notice, like after it's been wet and then you get the heat, then you get the humidity coming through and stuff.
Get that drive, yeah.
Just thank you so much, Tom. That was really fantastic and
Appreciate
great. Thanks everybody. It was a great crowd, great comments and questions. So thank you, everyone.